Hey everyone, the topic for today's video is electrical power. So previously we've talked about Ohm's law, which connected concepts of voltage, current, and resistance together. And now we're going to take it one step further and learn a little bit more about power. Before we get into what power is, let's do another review on our concepts of voltage, current, and resistance and really solidify those components in our minds of what they actually are. So voltage, if you recall, is the potential difference between the strength of the electron supply and the electron shortage. So it's basically that difference between how many electrons you have and on the supply and the shortage. And the greater that difference, the more voltage you'll have. And so the symbolic representation of voltage is a V. The units are joules per coulomb, or volts, which are voltage, which breaks down into a joule per coulomb. Don't just always just jump to volts. It's good for you to really understand what the units are when they break down. So a joule per coulomb being a volt could help you work problems in the future, understanding that a volt can be broken down. And then if we move to current, we have current is the net flow of electrons through a material. So basically it's the number of electrons that can pass a certain point. So the number of measured electrons that pass a certain point over time. The unit of a current is an ampere or an amp. And an amp breaks down into coulomb per second. If you recall, coulomb per second, a coulomb itself is a grouping of electrons. And so basically it's 6.24 times 10 to the 18 electrons. And so we're looking at a grouping of electrons passing per time when we're talking about current, because it's easier for us to see that grouping as opposed to one singular electron. If we looked at one singular electron, it'd be such a large number. And the symbolic representation for current is I. Then we move to resistance. Resistance is the measure of a material's opposition to the passage of electric current. So if you had just a wire with no resistance in it whatsoever, that current could just immediately go through. But if you had some type of resistive material in there, some type of like insulative material, then that current would have a little bit more difficulty just going from point A to point B. And so that amount of resistance that's put in there is a measure of resistance. And so we measure that in units of ohms, and it's represented with the Greek letter omega. And symbolically in an equation, you'll see resistance written as a capital R, which you can see in Ohm's law. So Ohm's law is a fundamental law related to electricity, and that relates voltage and current and resistance together. And Ohm's law is V equals I times R, which is voltage equals current times resistance. And basically it's saying that voltage is directly proportional to current and resistance. Now, if we go a little bit deeper with these concepts and we talk about power, we're looking at the work that is performed per unit time. And so it's a rate because it's per time. And so it's the amount of work over time. Work is represented, work is energy. Energy, and you might know from a previous class, energy is unit-wise is a joule. So if we're looking at a unit of energy per time, we're looking at a joule per second. So a work per time is a joule per second. And then you might have heard it more commonly referred to as a watt. So when you're buying light bulbs at the store, a lot of times you'll see that it works, how many kilowatts is a light bulb or something like that. And so you'll see watts a lot when we're talking about power. You might also see it in terms of horsepower. So horsepower is another way to write power. Horsepower is our US customary way of writing power. But typically for this class, we'll stick with watts. My question for you is looking at these units here and knowing that our goal unit, our goal is a watt, which breaks down to a joule per second. Can you see a correlation between any of the components? You might not use all three, you might just use two, but can you see how you can relate any of the two electrical components together and get a joule per second? And you can see, obviously, a voltage has a joule in its units. Volt has joule per coulomb, and it's in the numerator. And so that's kind of exactly where we would want that joule to be. And so we have a joule per coulomb with voltage. And then we also need time for power in the denominator. And we have coulomb per second for amps. And if I look at that, if I multiply those two quantities together, I can see that my coulombs will cancel out. And what am I left with? I'm left with a joule per second. So you can see that. So that is a coulomb per second, which is a current, an amp, a joule per coulomb, which is voltage. Your coulombs cancel out, and you're left with a joule per second, which is a watt. So we just derived the formula for power. The formula for power is current times voltage. So if you're calculating power, to help you remember the formula, just think, I've got the power. See what I did there? Let's work this problem together. So if we have a D cell battery, which is 1.5 volts, and it supplies 2 watts of power to a small bulb, I want to find the current through that bulb, and I want to find the resistance of that bulb. The current through the bulb, that's the first thing we want to find. So in order to find current through the bulb, we don't know the resistance, but what we do know is that there's 2 watts of power supplied to the whole circuit. So, and so if I know that there's 2 watts of power, then I know my power equation, power equals current times voltage. What I'm trying to find is current. So that's what I'm trying to find. I know power and I know voltage. So I can say that 2 watts is equal to current times voltage, which is 1.5 volts. I divide by 1.5 volts. And when I do the calculation, so it's good if you do work these calculations with me. So go ahead and get your calculator out and plug it in. I get current is equal to 1.333 amps. Now an amp is a coulomb per second. So just to confirm, what does a watt break down into? A watt is a joule per second, and a volt is a joule per coulomb. Now notice this joule per second divided by a joule per coulomb, the joules will cancel out. This coulomb comes to the top and you get a coulomb per second. What is a coulomb per second? Well, that's an amp. So those units work out. So that kind of confirms our derivation that we were able to get those units. So that's part A. That's the answer to part A. Let's look at part B. So part B says to find the resistance of the bulb. There are a couple of ways you can find the resistance of the bulb. You can use Ohm's law, or you can rearrange the power equation to have R in it. For now, let's just use Ohm's law. So we have V equals I times R. Our voltage is 1.5 volts. Our current is 1.333 amps times resistance. Our resistance then, when we divide by 1.33, so we do 1.5 divided by 1.333, and we get a resistance of 1.125 ohms. So that's just simply utilizing the power equation and utilizing Ohm's law equation. So I kind of alluded to this a second ago, in that maybe there's a way that we can represent the power equation, which is P equals I times V, in terms of R instead of having another term in there. So like, for instance, I have V equals I times R. That's Ohm's law, right? And then I know power is P equals I times V. Well, if I look at this V here and I look at this V here, the V in Ohm's law and the V in the power equation, are those the same V? Yes, they are. So if I'm saying V equals I times R, I can substitute in I times R for V. So I can say power is equal to I times R, which is that component there, the V equals I times R. And then I can simplify this and say power is equal to I squared, right? Because it's I times R. So this is a new form of the power equation. Maybe sometimes in your problem statement, you're given current and resistance, but you're not given voltage. And so if you're given current and resistance, you can still find power using this new form of it. Now, really all you need to know is these two forms, because you can get this version from these two forms like I just did. But it's also good to know that those forms are there and know that you can get those. So let me throw another question. Can you write power with voltage and resistance only? So basically I'm saying no current in the equation. Well, let's look at our equations again. P equals I times V, right? And so basically we're trying to eliminate current. Well, if I know Ohm's law right here, I know V equals I times R. If I divide R out, I can get V over R is equal to I. So now I can take this V over R, plug that in to I, and I can say P is equal to V over R times V. And then I can simplify that even more and say power is equal to V squared over R. So that's another form of the power equation. So now in this case, maybe you have voltage and you have resistance and you don't know anything about current. Well, you can still find power. We have Ohm's law, which is voltage equals current times resistance. We have voltage, current, resistance, and we've introduced a new quantity, and that's called power. Power is represented by a P in equations. The units of power are watts. A watt breaks down into a joule per second. And the equation for power, or you can represent power by multiplying current times voltage, or voltage squared over resistance, or even current squared times resistance. So there's three forms of that power equation. And something that I think is really neat to note, if you have any two, you can get the other two. If you have voltage and current, you can find resistance and power using using the power equations or Ohm's law or some form of both of those. If you have resistance and current, you can find voltage and power. If you have power and resistance, you can find voltage and current. So as long as you have two, you can always find the other two.